So the formal method of integration by parts will always work, but it is slow, especially if you have to do it multiple times, like the second, or like the last example I did, or example number 2 I did in the last video. Uh, so there is a method called the table method for integration by parts, which is much, much faster. However, it doesn't always work. So like example number 3, this would not work in example number 3. And in our special cases, you'll see it won't work in our special cases. So the idea of this is I've checked to see if I know the antiderivative directly. I don't. I've checked to see if chain rule is involved, and it would really be integration by substitution, and it's not. So now I'm thinking product rule and integration by parts. And in this case, U has to be something that derives down to 0. It's not a preparation. It's not preferred like with the formal method. The table method, it has to derive down to 0. And the other part has to be something I can integrate repeatedly, relatively easily. And so what we do is, if I look at the same problem I did for example 2 in the last video, x squared e to the x. I don't know that antiderivative directly. I don't see anything inside of something else to make me think I have to undo chain rule. So I'm at product rule. If I say u is equal to the x squared, and then dv would be the e to the x dx. Actually, you'll normally see me just write it as e to the x. In the first column, I'm doing derivatives until I get down to 0. So the derivative of x squared is 2x, derivative of 2x is 2, derivative of 2 is 0. Once I hit 0, I stop. And then I do antiderivatives in this column. Antiderivative of e to the x is e to the x. Antiderivative of this e to the x is e to the x. And the antiderivative of this e to the x is e to the x. I then am taking the first row, first column, times the second column, first row, or times the second row, second column. So it's always offset by 1 row when I move from first column to second column. So first column, first row, second column, second row. And I want the positive value of whatever I got. Or I should say, I'm going to have a plus whatever this product is, not the positive value, plus whatever this product is. So I have x squared e to the x. Then I have a minus sign, 2x times e to the x, plus 2 times e to the x, and then because this is indefinite, plus c. And there's my antiderivative. For this example, you'll see it go a little bit faster, kind of how it's done this way. When I look at the integral of x cubed sine of x, I do not know that antiderivative off the top of my head. I don't see anything inside of anything else to make me think I have to undo chain rule, so it's not substitution. So I'm thinking I have to undo product rule. I'm going to say that u is the x cubed, and dv is the sine of x. I'm going to derive the x cubed down until I get to 0. And I need antiderivatives for the dv column. So the antiderivative of sine would be negative cosine. And if I check that, derivative of negative cosine would be positive sine. Antiderivative of negative cosine is negative sine. Antiderivative of negative sine is positive cosine. Antiderivative of positive cosine is positive sine. I then want to multiply by 1 offset row. This will be the plus, minus, plus, minus. And I just alternate plus, minus as I go down that, starting with plus. So I have plus the x cubed times negative cosine of x minus 3x squared times negative sine of x plus 6x cosine of x minus 6 sine of x and plus c because it's an indefinite integral. And that is much, much faster, because otherwise this would have taken three of the formal ways of doing integration by parts.